So namaste everyone. I'm Dr. Lavanya Hegde. I welcome you all for engineering geology class sessions. So today we are discussing part 4 of module 4 hydrogeology. Under this session, today we are discussing something about artificial recharge of groundwater as well the rainwater harvesting techniques. In previous sessions we have already been discussed where is the earth's water, what is the quantity of usable quality of water we have been discussed. So friends, we already know that the distribution of the water on the earth's surface is extremely uneven. Only 3% of the water on the surface is fresh. The remaining 97% resides in the ocean. Of this fresh water, 2.5% of fresh water, 69% resides in glaciers and 30% in as underground. Only less than 1% is located in lakes, rivers and ice. So we have discussed the global fresh water that can be accessible for the usage of mankind is only less than 30%. This is the scenario of the availability of water, but demands in various sector is increasing. This figure shows the demands of various sectors like irrigation. Maximum water has been or the demand for water in under various sector. Irrigation consumes the maximum quantity of water. The domestic usage next, and industries use are in third place in the usage of or demand for water. And see, the environment and evaporation losses are neatly explained in this figure. So now, how much natural resources we have? Annual precipitation for us in India is 4,000 billion cubic meters. Available water resources are 1869 billion cubic meters. So utilizable quality, how much it is means, so it's nearly equal to, approximately equal to 1123 billion cubic meter. So in that, surface water is 690 billion cubic meters and groundwater, which can be which is replenishable, is 433 billion cubic meter. So what are all the groundwater resources we have? Annual groundwater recharge in India is 433 billion cubic meter. Net annual groundwater availability in India is 399 billion cubic meter. So groundwater draft 230.58 billion cubic meter. And nowadays the stage of groundwater development is almost 62%. Means people are reliable on this groundwater compared to the surface water. So stages of groundwater development before 1991, it is comparatively less, that is 32%. 2004 it's 42%, and in March, okay, it's 58%. Okay, March 2004 it's 58%. Now it is more than 62%. So what is the per capita availability? This graph clearly shows there is minimum quantity, less quantity of water is available, and it is going to decrease year by year. That is per capita availability of water is so less than 1000 cubic meter per year, okay, is available in 2050. And this picture nicely explains what we have with us. The crisis, rapid and accelerated development has led to the crisis or to the stress on groundwater resources. Depending on the groundwater levels, deepening of the groundwater levels, increased energy consumption, adverse environmental impacts and resource crunch, imbalance of the groundwater system, quality problem, threat to groundwater sustainability. These led to the crisis of groundwater. Then what is the solution? So conservation and replenishment are the main types of solutions for this problem. So what is water conservation? So water conservation is the practice of using water efficiently to reduce unnecessary water usage. We use water, we misuse water, we overuse water, we abuse water. So we have to stop misusing, abusing, overusing, all these different usages. Okay. So wherever necessary we have to use the water. According to the freshwater watch, the water conservation is important because fresh clean water is a limited resource and as well as it's very costly one. So water conservation refers to the preservation, control and development of water resources, both surface and groundwater, and prevention also the pollution. Then artificial recharge and rainwater harvesting are the two main answers for this problem to meet the scarcity or to meet the demand. Artificial recharge is a process by which groundwater reservoir is augmented at a rate exceeding that under natural conditions of replenishment through suitable civil structures. Rainwater harvesting is the technique of collection and storage of rainwater at surface or in subsurface aquifers before it is lost as subsurface runoff. So any man-made scheme or facility that adds water to an aquifer may be considered as an artificial recharge system. So why this rainwater harvesting and artificial recharge? So to arrest groundwater level decline, to save the energy, to mitigate flash floods, soil erosion, silting of reservoirs and rivers, to control salinity increase and saltwater intrusion in coastal areas, to improve the river generation for sustainability of groundwater supply sources. So what is artificial recharge? Already we have explained. It's a process by which groundwater reservoir is augmented at a rate exceeding that under natural conditions. So artificial recharge is a practice of increasing the amount of water that enters the aquifer through human controlled means. For example, groundwater can be artificially recharged by redirecting the water across the land surface through canals, infiltration basins or ponds, adding irrigation furrows or sprinkler system, or simply injecting the water directly into the subsurface through injection wells. And now let us discuss site selection for artificial recharge. The artificial recharge projects are site specific, and even the replication of the techniques from similar areas are to be based on the local geological and hydrological environments. The first step in the planning of the project is demarcate the area of recharge. So area should have the aquifers with high porosity, and the area should not be get polluted, surface pollution should not be there, and the area should receive good amount of rainfall, etc. are the first step of planning. So the artificial recharge of groundwater is normally taken in following types of areas. Areas where groundwater levels are declining on a regular basis. Areas where substantial amount of aquifer has already been desaturated, and the areas where availability of the groundwater is inadequate in lean months. So areas where salinity ingress is taking place, that is in coastal tracts, wherever the saltwater intrusion taking place. These are all the areas where the artificial recharge should be taken. What are the evidential themes for this site election? Geology, geomorphology, land use, land cover pattern, the soil type, the slope of the area or gradient of the area, availability of the surplus runoff, identification of suitable hydrogeological environment. So in this hydrogeological environment, we have to consider the vadospace, porosity, hydraulic conductivities like transmissivity, permeability, storage coefficient, depth of the aquifer from the surface, and depth of the water table in pre-monsoon times and post-monsoon times. So long-term water level trend we have to discuss before, or we have to understand before the site selection. The need is need of that area or that site, that is availability of beneficiary group who are there, who are all the type of people residing in that area, what is the economy of that people residing in that area. All these themes are evidential themes in site selection for artificial recharge. Okay. So let's discuss some of artificial recharge techniques in hard rock area. Contour trenching or on hill slopes, contour bunding, gully protection or gully plugs, nala bunds, check dams, percolation tanks, point recharge structures, recharge through dug wells and as well bore wells, recharge shafts, subsurface dikes and groundwater dams. These are all the different types of techniques which has been used in hard rock area. So let us see one by one the types of recharging techniques. Contour bunding. Okay. So this type of bunds are constructed on the sloping ground all along the contour of equal elevation. So water conservation measure to slow down the runoff in these areas and thereby causing the more infiltration in that area. Flowing water is intercepted here before it attains the erosive velocity by keeping the suitable spacing between bunds. Lands with moderate slope, spacing between 2 CB depends on the, CB means contour bunds here, depends on the slope of the area and permeability of the aquifer or the soil in that area. So this is a sectional view or schematic view of contour bund. Here in this picture photograph, it is well shown here. See the contour bunds created to check the velocity of water, thereby facilitating the infiltration. Gully plugs or bunds. Using locust stones, clay and bushes across small gullies and streams, that streams of first order and second order, these gully plugs or bunds have been established. So water conservation, it's a water conservation measure to slow down the runoff and thereby causing more infiltration. With the help of gully plugs, conservation of soil and also the soil moisture can be conserved. Whenever there is a local break in the slope to permit accumulation of adequate water behind the bunds, so gully plug method or bunds method have been used. So this is a gully plug. Nala bunds. These are the embankments constructed across the nalas for checking velocity of the ground runoff, increasing the water percolation and improving the soil moisture. Nala bund is generally a small earthen dam. In Kannada we say oddu. Okay, with a cut off core wall of clay or brick through the cement bunds. Though cement bunds and plugs are now prevalent. Nowadays cement plugs and plugs people use, but in earlier days the clay or brick walls have been used. It's a kind of gabion is a kind of check dam commonly constructed across a small stream to conserve the stream flows with practically no submergence beyond the stream course. Okay. So boulders locally available are stored in a mesh of steel wires and it is properly anchored along the bank side to avoid the washout during the peak rainfall runoff, okay, or rainfall. The height of such structures are around 0.5 meters and the stream width should be less than 10 meters. Suitable, it is this type of structures are highly suitable for hilly regions and forested areas having large number of small streams. Excess water overflow overflows this structure, storing some water to serve as source of recharge. Silt content of the stream were deposited in the interstices of the boulders in the due course. So with growth of vegetation, the bund becomes quite impermeable, okay, by this silt deposition, and helps in retaining the surface water runoff. So this is a gabion structure. Boulders are trapped or kept inside a steel structure or steel mesh, and they are constructed across a small streams. Check dams are the structures constructed across small streams having moderate to gentle slope. Height should be approximately 2 meter. Side should have sufficient thickness of permeable bed or weathered formation to facilitate the recharge of stored water within short span of time. That means the aquifer should be having a great porosity and highly weathered system. So water cushions are provided at the downstream side. The total catchment of the Nala should be 4200 hectare, rainfall less than 1000 millimeter, and width of the Nala bed should be 5 to 15 meter, and depth of the bed, the check dam bed, should be greater than 1 meter. The series of check dams can be constructed to have recharge on regional scale. So this is the photograph of check dams. You may have observed in your areas also. So vented dams constructed across the streams in moderate slope hilly areas. The height of the dam should be less than approximately near to 2 millimeter. The total catchment of the Nala is 4200 hectares, and these are all high rainfall areas. Where the high rainfall areas exists, these vented dam work out, and width of the Nala bed normally 5 to 15 meter, and depth should be more than 1 meter. Percolation tanks. This is an artificial recharging body or artificial surface water body, preferably constructed across third and fourth order streams, wherever the gentle slope exists. Normally these are designed to storage 0.1 to 0.5 million cubic meter of water. So mostly these are the earthen dams with masonry structures only for the spillway. Point recharge structures or PRS. So these are PRS are the structures that can be anything from a small pit or simply dug pit into a soil, or to a borewell converted for recharge. So what are all the advantages for this point recharge structures? Let us see. So recharge through deeper fractures feasible from these point recharge structures, and improvement in the yield of borewells, improvement of groundwater potential can be reached by this method, and structures are simple and easy to construct. Abundant borewells will become functional borewells. These are all some photographs showing PRS, okay, in hard rock terrain. The recharge of open well in charnocite terrain. This open well is where the rocks are highly fractured. So then recharge shaft. This is a very much cost effective technique to recharge unconfined aquifer overlain by poorly permeable strata. Where the permeability of the strata is less, this type of technique has been used. The diameter of the shaft is normally more than 2 meter, and the top of the shaft is kept above the tank bed level, preferably at half of the full supply level. In upper portion of 1 to 2 meter depth, the brick masonry work is carried out for the stability of the structure. This is recharge shaft structure in vesicular basalt terrain. It's a photograph showing recharge shaft. So this is recharged to open well. A filter unit is established to clean the water from the roof. This is an open well recharged. So recharge through borewell. Here the water has been stored at some place. The runoff has been stored, and there should be a silt barrier, and it may be a wire mesh or impermeable mesh or biological membrane like that, and this is connected to this coarse sand and gravel. Here it is once again filtered, and then it is having connection to the borewell. All the photographs showing borewell recharge. So this photo shows borewell recharge work filtration in media installation, the recharge borewell structure. Let's move for next type, that is subsurface dikes. Subsurface dikes are suitable for valley and streams in hard rocks where the base flow is available for longer duration in the stream. Impervious layer exists at a shallow depth. Here the trench is excavated across the stream up to a depth of impervious layer, and it is backfilled with clay or other impervious material. In the upstream side of the subsurface dike, groundwater level will rise, and it can be extracted by making large diameter open well. So it is suitable for valley and stream having base flow for longer duration. Approximate cost may be up to 2 lakhs to 1 lakh. Subsurface dikes. This is the figure showing surface. Here trench has been excavated and filled with impermeable material, so that these areas will be saturated with this stream water. So this is regional water table, but when the subsurface dike has been created, this is the water table elevated from regional water table due to this subsurface dike. These subsurface dikes received considerable attention in recent years. Nowadays, it forms a useful structure in areas where the rainfall is concentrated for few months, which is followed by the prolonged dry spell. Useful structure where the groundwater is stored in the aquifer itself, and it is a conservation, very good conservation structure. The identification of the site is important criteria. Here it's a difficult criteria. It should be done by the experts only. These are the photographs showing how the shafts have been created. So these trenches have been filled with impermeable material, concrete material, to construct a barrier between upstream and downstream. How should be the geological terrain for artificial recharge techniques? What are all the techniques which are viable at hard rock area like igneous and metamorphic terrain, and in unconsolidated area or soft rock, or in alluvium? What is the slope zonation we have to use in different types of sites? Steep slope, moderate slope, gentle slope, or moderate to gentle slope. So in hard rock terrain watershed, on the basis of thickness of the phreatic aquifer, area has been differentiated into different types of zones. It is these different types of zones are dependent on the thickness of the aquifer, slope of the area, and water table fluctuation with the seasonal climate or with time. So there are runoff zones, piedmont zones, transition zones, and storage zone. So in runoff zone, slope is 10 to 20 degree, and these are highly weathered. They are not, these are very thin or not developed properly. Okay, and water conservation structure to be taken in this hard rock terrain are where the runoff zone is there: bench terrace, contour trench or burn, gully plugs and gabion structures. In Piedmont zone, we have to go for contour trench or bunds, nulla bunds or check dams, diversion weir and percolation tank. In transition zone, the slope will be less than Piedmont zone or runoff zone, that's 5 to 2 degree, and water table fluctuation is moderate here. The structures to be constructed here are check dams, shaft, nulla bunds and recharge pits or subsurface dikes. In highly weathered hard rock terrain, that is storage zone, slope will be less than 2%, and the thickness of the aquifer is highly thick, and water table fluctuation is very less. The structures suitable for this type of zone are irrigation tank, flooding and farm pond. These are the techniques to be used in soft rock or alluvial terrain. Okay. Flooding, ditch and furrow method, recharge basin methods, stream modification, surface irrigation, recharge pits and shaft, induced recharge are the main methods used in soft rock terrain. So this is basin method, and in this method it involves surface spreading, okay, of water in the basin that are excavated in the existing terrain. The size of the basin depends on the slope and the land surface. Infiltration rate increases with the depth of the ponding. In alluvial plains, the water may be diverted into one or more basins constructed parallel to the stream, okay, here, parallel to the stream or the stream channel. The basins are constructed in pair or in series. The upper one serving as a settling basin for removal of silt. For effective artificial recharge, highly permeable soils are required, and maintenance of the water layer above the soil water is very much necessary in basin method. This is ditch and furrow method. In areas with irregular topography, shallow, flat bottomed and closely spaced ditches or furrows provide maximum water contact area for recharge the water from different types of sources, stream or canal. This technique requires less soil preparation than the recharge basins, that is previous method, and it is less sensitive to silting. Generally, three patterns of ditch and furrow system are adopted: lateral ditch system, dendritic pattern and contour pattern. So in lateral ditch pattern, the water from stream is diverted to the feeder canal or ditch from which the smaller ditches are made at right angles. So in dendritic patterns, the water from stream can be diverted from the main channel to a series of smaller ditches which will spread in a dendritic pattern or tree-like pattern. In next or third pattern, that is contour pattern, here the ditches are excavated following the ground surface contour of the area. When the ditch comes closer to the stream, a switchback is made, and thus the ditch is made to meander back and forth to traverse the spread for repeated times. So maintenance of these recharge structures, initial planning has to be done for maintenance of recharge structures. Provision to be made in the proposal stage, okay, planning stage itself. Beneficiary can do maintenance. What are the beneficiary group or the people of that area where the recharge structures has been take place? They can be the in charge of maintenance, and they can take care of these structures. people of that area should have awareness for maintenance. That can be done through public-private partnership. These are all some findings of artificial recharge structures. Percolation tanks. Here improvement in tank bed percolation is due to desilting, improvement in groundwater level up to 2 to 4.5 meters. Change in cropping pattern. Silt is used as manure. Generation of rural employment can be improved by this. So watershed treatment technique provides it will lead to surface runoff, less surface runoff, and it can be built in groundwater levels. So improvement in the productivity of borewells, prevention of soil erosion you can achieve by this structure. Point recharge structures. Here the recharge through deeper fractures is feasible. Improvement in the yield of borewells can be achieved. By the improvement of field of borewells, the potential of groundwater is increased, and these PRS or point recharge structures are very simple and very easy to construct. Roof top rainwater harvesting. So cost of harvesting is very less here. Existing well or borewell can be used, and it prevents once again surface runoff. The gravity recharge experiments proved the possibility of recharging the fractured aquifer with an intake of 3 to 4 IPs in granites and gneisses, and it can be made operational if source water is available. So that's all. Thank you once again. Let's meet in next session.